Ladies and gentlemen, hello and welcome back once again to the Bloor Group Research webcast series. My name is Eric Cavanaugh. I'm going to be your moderator for today's event. Folks, we've got an all-star cast lined up calling it from all around the country. We've got our very own Dr. Robin Bloor. We've got representatives from CASC, Cambridge Semantics, and Unify, and we have our good friend Eric Little dialing in. It's going to be an all-star cast telling you all about the data lake. This is good stuff, folks. Thanks so much for your time, and let's dive right in. So, there is a slide about the different participants. Hit me up on Twitter at Eric_Cavanaugh. You can see my email address there as well. An easy one to remember is info@insideanalysis.com. And if you'd like to tweet, go ahead and tweet with the hashtag of data lake, and we'll try to track that live during the show. So we take a different approach to many firms with respect to primary research. What we like to do is have a series of webcasts. The first one was last year, frankly. We did some interesting stuff to understand where things are going. And basically the exploratory webcast is designed as a way for the analyst to throw out a hypothesis, to say, here's what I think is happening, here's where I think the market is going, here's what I think is going to happen, what we'll find in the research. And then, of course, during the process of research, we learn a whole bunch of other stuff. We talk to various experts in the field, we get some candid opinions about what's going on, what their perspectives are, and we try to dig deep into the technology stack, because, of course, that's where we focus our attention to help companies understand what these different platforms are, how to use them, when to use them, where to use them, when not to use them, what they don't do. I've always been impressed by software vendors who will come and tell you that they do X, Y, and Z, and they don't do A, B, and C. So it's important to understand what software packages do, and it's also equally important to understand what they don't do, because oftentimes you may go out and buy a software package thinking it's going to do various things and finding out later that it doesn't, and that is not a very pleasant experience. So today is the roundtable webcast. Like I said, we've got all these different experts on the line today. We're going to give their perspective on the data lake, and then a findings webcast will be held next month. So with that, I'm going to hand the keys over to Dr. Robin Bloor. Stand by. Take it away. And like I said, folks, tweet with the hashtag of data lake. We'll be tracking that and watching in real time. So take it away, Robin.
Okay, well, thanks for that introduction, Eric. What I'm going to do really is say where our thinking is at this point, which is very close to the end of the research that we're doing, but there are other things that I've yet to do to kind of firm up on it. So I'm going to, in one way or another, I'm going to present what we think a data lake is at this point in time, not so much what you can do right now, but to a certain extent where we think it must inevitably go. So first thing to say, this is really the whole thing that's happened with big data is really based around parallelism. We used to see, as analysts, we used to watch expecting an increase of about 10x performance improvement every 6 years, and that would bring new technologies to the market, new software, and so on and so forth, making changes to old software. Now we're seeing 1,000x, and that's just an approximation. Depending, the level, depending on how much iron you want to throw at something, you can make, you can reduce latencies to things that were unthinkable 5 years ago. The scenario out there, the thing that's still uncertain. Two aspects to it, hardware and software really, but things that are uncertain. We're not really sure where technology is going to go. The thing to say about hardware is that all the bits in one way or another become way more confusing than they used to be. We used to think in terms of there being, a CPU and memory and disk, and that was kind of it. And that's no longer the case. Now we have CPUs, GPUs, and FPGAs. We have the cross-breeding of those things, chips coming out with mixed CPU with GPU or CPU with FPGA. We've got system on a chip initiatives going on. We've got a new kind of memory, 3D crosspoint, or PCM is IBM's. We've also got the memory store from HP that hasn't kind of made it to the market yet, but is going to, or HP say it is. We've got solid-state disks, including those with parallel access, that have got way much faster ability to retrieve data than we ever had before. And we've got parallel hardware architectures, and we've got a number of initiatives in the market where people are actually building new configurations of hardware to achieve specific workloads. So we've got a much more mutable hardware world than we ever had before, and we can make it all go parallel just by clipping lots of it together and wiring it all up. If we now go to software factors, we're witnessing the triumph of open source as a business model in the sense that pretty much the whole of what's happening in the Hadoop Plus space, the big data space, is now being driven to a fairly large extent by a number of companies that have demonstrated successful open source business models. So it's not just Red Hat anymore, is basically what's being said here. The dominance of Apache, you've got Hadoop and, as a platform for data, plus all of the components that are in the Hadoop ecosystem, because you've also got Spark, which is a separate initiative, and that has a series of components. And we've recently had the advent of Kafka and Unify for data connectivity come to the market. And that's created a stack of software, the like of which we've never seen before. I was inclined to think of it as a distributed operating system for data, and I'm still inclined to think of it as that, but I'm still not sure that that's what it is. We're witnessing the triumph of the cloud at the moment and its dominance. Apparently 30% of big data projects are actually cloud projects now. Big data has in a large way gone to the cloud or split itself between the cloud and on-site. We've got little data is also big data. That's just the point that there's an awful lot of this is very useful even if the data isn't measured in, you know, hundreds of terabytes or petabytes. You know, small amounts of data with its tiny technology sitting underneath it, you can do a lot with that. Cost challenges, there's a couple of cost challenges. One is the cost of actually making all of this, fitting all of this together in a workable way, and it's not a trivial thing to do. It's easy to get the pieces, but it's not necessarily easy to fit them together and make workable systems from them. And the cost there, the software doesn't cost a lot, but the cost of actually together can be great. But then you've also got the cost challenges to the big database vendors that, you know, making such a living out of data, and the data lake is becoming the data warehouse, so that's a huge challenge for them. Because as long as you do it in a sane fashion, it's way, way less expensive than big data warehouse technology. Everything in flux, this is just to say, you know, look at what's changing. Hardware is changing all over the place. Number of data sources, well, that's changing. The way that we stage data into an organization, it's now the data lake, so that's changing. Data volumes way, way different than they ever used to be for some organizations, very large data volumes. Data flow, far more amount of data flowing from one place to another than there ever used to be, plus the need in a lot of circumstances to process the data in motion. Data governance, which was hardly talked about 15 years ago, has now become a huge thing. Data usage, you're getting usage of data in applications that we've never seen before. I mean, machine learning was the beginning of that, but there's an awful lot. Well, new things seem to happen every few months, you know. Data structures, we've now got the merging of all data structures into a single store in the data lake. Different approaches to schema definitions and data definitions. Ingest speeds getting higher and higher, and data workloads getting greater and greater. Everything's in flux, and that's why my guess is that when we write the report at the end of this research, we'll still have to put in a fair amount of caveats as to what we really mean. So I'm now just going to define what I think a data lake is. There's a lot of slides here, but I created a lot of slides just in case anybody wanted to keep them all and start thinking about them on an individual basis. Because really, all of this could have been put on one diagram, and I've got about 9 slides for it. I'm basically saying in outline, if you have a data lake, there should be data staging and ingest going on. There should be data governance happening. There should be various kind of data applications. And you should have an export capability to take data elsewhere. It's a trivial thing that's being said here, but you know, you've got to define your terms. If we do in greater detail, this is the bigger diagram that I'm currently working with as it's kind of future of data lake rather than the initial current instantiation of it, although there may be companies out there that could do most of this, and certainly the companies who've got sponsors are very capable of putting together a fairly robust configuration. But point here is that data lakes are complex in respect of the necessary components that they must have. Not that, are nice to have, but that they must have. Data ingest, the only point being made here is that there's a data bus involved in this. In other words, data ingest can be a whole series of requests sent to Kafka or Unify, which is two complementary ways of pushing data about. You've got all of these data sources, servers, desktop, mobile. I mean, just everything that you can imagine can be a data source pushing data into the lake. We've got the possibility that there may be some real-time applications that you absolutely have to allow access to the data before it might even be properly ingested in terms of the data governance you want to do, simply because the latency required is so low for them to deliver the value that they're doing. So you've got this, yes, there's going to be real-time apps, and they may be looking at data, and obvious applications like predictive analytics fall into this sphere, but there's an awful lot more than that. There's things like, in certain situations, you're going to want to be looking at the stream of data coming into the organization and initiate alerts to applications or to various people in the organization because certain thresholds have been violated. So real-time apps may need to have priority over data governance, and all that's telling you is that the architecture is not going to be simple. Some data governance may need to be reapplied in real time, and again, this is while you've got the data flying around, if you can do things that you will need to do to any of the data that's coming in, think of it as a stream of events, then you may as well do it on entry. So what I've got here is transformations and aggregations, metadata management, deducing metadata where you need to, data cleansing, some data cleansing, but absolutely not all of it can be applied to a stream as it enters the lake. And certain security things, particularly encryption, can be done on entry to the lake. But this isn't to say that these processes must be done in real time. It's just that some of them can. And if you can, in my opinion, at some point in time, the technology will be so fast that people will. In terms of governance, well, obviously it needs to happen within the lake as well as on entry to the lake. So all I've done is added all of these things as processes that will possibly be happening in the lake. Plus, you've got life cycle management added to that. And I could have broken these out or broken these down and added a number of different terms. I could have had specifically provenance and lineage and things like that. But what I'm really doing here is just these are the big pieces, and most of everything else that's going on could be attached to any one of them, or to at least one of them. So I'm saying if data governance was important before big data, and it was, although it wasn't a lot of it that was done, it's far more important in the era of data lakes. And the reason it's really important is an awful lot of data flow going around. And if you're going to say what needs to be governed, just this slide makes one point and one point alone. The data at rest needs to be governed, and the data that's flowing around needs to be governed. And it needs to be governed from soup to nuts, from the beginning to the end. Well, what is data governance? Well, data flows and data storage, it applies to. Security and access is governance. Data cleansing and transformations are governance. Data meaning is governance. Determining meaning, which is metadata or metadata beyond metadata. I mean, ultimately, if you extend metadata, you end up to its logical conclusion. You end up with data meaning. Data provenance and lineage, data archive and disposal, and the management of availability and performance. To you're going to have to use the technology to do all the kinds of replication and disaster recovery that any other system needs. Data lake apps, this is a simple thing really, because I'm not going to talk in any detail about analytics. The data lake is ultimately an application platform, so you can put a lot of things on it. But one of the things that really ought to be there is a search and query capability, so you can see exactly what's in the lake, and so that people can explore the lake or explore the parts of it to which they have the right to look at. And then obviously there's going to be BI visualization and analytics applications that run against the lake. And there's other apps that people will dream up that possibly wouldn't be classified as in the the feedback stuff of BI and analytics. And then there's going to be extract, you could call this ETF if you wanted, but extracts of data from the lake to go to other places. The idea that the lake will be the only place where applications run, even if the lake was perfectly scalable to infinity, it probably wouldn't be practical to do that. Logical data lakes, I presented it all as if it was a physical model, but really what I presented was a logical model. And we will soon be speaking of logical data lake and multiple physical data lakes, because the way I see it is you can't necessarily balance those workloads over a specific single expansible of hardware, and therefore the easiest way to actually attack that will be to have multiple physical data lakes. But in doing that, you're going to want to be able to look at it as a single logical data lake. And that's going to involve imaginative uses of Kafka, or, well, imaginative data streaming, Kafka, Unify, or if you use MapR, then the inbuilt streaming in MapR. So this is the data lake. This is what I'm saying a data lake is right now. And if I was to say what it actually means, it means it's a staging area for all new data, internal or external. It's the primary domain for data governance. It creates the system of record for an organization. It is an event data warehouse, and it is an environment for user-defined self-service. If there's anything else, I haven't thought of it, but there may be other stuff. And the final point is, data warehouses are important. A lot of things happen around data warehouses. In my view, a data lake is much, much more than a data warehouse. I think I've finished. Is the jury still out on data lakes? Lessons from the biotech industry. It's not me speaking about this. It must be Eric Little.
And with that, I'm going to hand the keys over to Dr. Little. Stand by. There you go. Take it away.
Okay, thanks very much. Robin, that was a great intro, and I'm going to basically build off some of those concepts in there because I'm in fairly strong agreement with several of the points that were made in the previous slides. I would also like to say I'm going to put a little bit of skepticism into data lakes, only because I don't think that there's skepticism around them existing. I think there's skepticism around simply the buzzwords that people are using to describe them. And so I'm going to talk a little bit about some of our customers and the lessons that we learn at OSTHUS in the biotech and pharma industry. So a question I get asked a lot at either university types of talks or from some of our customers are the kinds of things that say, well, what are data lakes and why are they all the rage? And really, as Robin pointed out, data lakes are centered around big data. They utilize extensive cloud technology, primarily for a lot of scalability. And the scalability is really around a lot of types of data. So on this slide, what this is meant to show is that you have some folders with unstructured data. You can have different kinds of databases like graph databases, and then you can have your structured databases, and you can have semi-structured things. And the idea is you're pouring all of this into one area, one place in your organization. And by avoiding the strong kind of ETL processing that goes on in data warehouses, people are enamored with the fact that your raw data will be more available to people over time, so as your needs change and as your query patterns change, that data will be available to you to use and to answer some complex questions in your business. And so what we see is we see a lot of extensive user access across these kinds of organizations that want to tap into the data lake. So data lakes, because they contain these numerous types of data, the question does become, how do you maintain them over time? And one of the problems is, because the data is not transformed via some type of a standardized ETL, you have this issue of not always knowing what's in there. So while it can slice and dice a lot of different ways.
Conference recording has stopped.
Lots of information out. Hello?
Go ahead, that's your backup.
So while it can be sliced and diced in a lot of different ways, the issue here is that how does one maintain this information over time, and how do you even know what's exactly in there? So that's quite an interesting set of problems that this new kind of technology raises. So a lot of people who talk about data lakes, or if you go to a lot of the conferences, you'll hear this term of a data swamp. And so I wanted to touch on this for a moment because I think if done poorly, a data lake becomes that. It becomes a quagmire of your data. And so the reason that data lakes exist is to really store massive amounts of raw data cheaply. Data warehouses have a lot of structure behind them, and as most large organizations have discovered over time, they're quite costly to build and maintain, and there's an argument that they're never actually finished. So the idea is instead, well, if we pour everything into this lake and we don't pre-process everything, we somehow save a lot of money, and we can store a lot of stuff much more cheaply. So the problem, though, is that what you're doing is you're pouring all of this information into one bucket. It would be like having a closet in your house that you put everything in, your kitchen supplies, your coat, your boots, your car keys, your television remote, everything goes into one closet. And then the question is, okay, well, over time when that fills up, and I want my bowling ball or I want my golf clubs, how do I find these things? Because I have this massive pile of information and I've not really bothered to put shelving in there so the things aren't neatly organized because I didn't want to spend all that money, and I didn't want to build the shelving one way and then say, well, it doesn't work for me after a while. I have to rebuild the shelving over and over and over. That's the argument against the data warehousing approach. So if I have this closet, right, and I have all my information in there, or all my possessions, it could be really hard to find the specific thing I want. And in fact, over time, if other people are putting things in my closet, I may not even know someone put my golf clubs in there. So this is a problem that people have oftentimes with data lakes is the third bullet that reads, the schema on read. This can be really computationally problematic. And the reason it can be computationally problematic is that if there's no structure, if I don't know what's in there, and I start writing queries against this data lake, as we've seen some of our customers do, the queries may produce zero results, which means, okay, did I write the query wrong, so there's data in there, but I simply didn't get the names of my entities correct, or I didn't do all of my, I didn't write my query properly, or is it that there's really none of that data in there? Or worse yet, if I get information back, did I get all of the information back, and how do I know? How do I even check that? So this can be really hard to manage over time. When Robin said that data governance is of utmost importance, I couldn't agree more. The management of how the information goes into the data lake and the management of the way you're going to query it and pull things out over time and the way that you're going to track the provenance of your data lake is really, really important. And so the question becomes, how do you know or test what's actually in there because you've built this large schemaless kind of entity? So to get value out of this, right, you hire data scientists. So the joke that I have in this slide here on the right-hand side is some of you may remember that the Harvard Business Review wrote an article that said data scientist is the sexiest job of the 21st century. And my rejoinder to that is not if you have to clean up a data swamp. It's not necessarily such a great job to have. But the answer, realistically, is that you have to have now specialized kinds of individuals to help manage these things. And why? Well, because as Gartner points out, that the proposition of enterprise-wide data management has yet to be realized in this technology. So there are several of the large technology consulting firms who are writing a lot of these articles saying, okay, well, people are spending all of this money, they're building a lot of data lakes, but the answers are not flowing out of these things willy-nilly. In other words, the data lake isn't producing what we thought it would. It's not the silver bullet we thought we were paying for. And so managing these things is very, very problematic, especially if you don't have the right people in place. Governance, as we've already said, is a big issue. The data lakes are best used by these kinds of specific trained individuals, namely data scientists. So you need to find people now who can have a applied mathematics background, who can write fairly complex algorithms, who can do a lot of massaging of things, who can actually look at trends and patterns in your data and help to determine what's in there and write indexing strategies around how to get things in and out and so on. So it's not meant to be used really by an entire enterprise. And I think that's a key issue here in the governance. Many people think we're going to build this data lake and we're going to open it up to the masses and let everyone use it. And our experience in this space is that's a pretty bad idea. You're going to want some power users, and you're going to want to build app stacks and things on top of it that allow people windows into the data lake and perhaps to use the data from the data lake inside of other applications, but turning your data lake free on your organization and making it the wild, wild west probably is not going to have good results. And the customers we're engaged with have really varied results with their data lakes. So the ones who tend to have the most success, they put some kind of lightweight schema in place. Somewhere between what I would say a heavy ETL like a data warehouse and nothing. So the idea of having completely schema-less data lakes, I don't think that's entirely possible. In fact, I think that based on the experiences that we've had with our customer base in pharma and biotech, is there has to be some structure in there, but the key is that you want it to be flexible. So what do we mean by flexible? Well, maintaining a data lake with a lightweight, manageable schema oftentimes winds up being a good idea. And so a semantic approach to metadata, so Robin mentioned in his slides the meaning of the data, and I think he's right about that. In fact, some people, and I know Cambridge Semantics is going to be speaking in a moment, and I think they'll also agree with this, the notion that smart data lakes make a lot of sense. So you have to put some kind of intelligence around this thing while not trying to over-architect a data warehouse so that, you know, your data is built for one specific set of purposes or one or two areas of your business but no one else, or a specific set of queries or what have you. And using semantics in this way, you can avoid a lot of the machinery by keeping your models lightweight, keep them very conceptual in nature, and keep them about the most important things, make them highly customizable. So you should have various groups be able to put their conceptual models against the data in a fairly straightforward way. The data model should be separated from your raw data. That's a basic tenet of using some kind of a semantics. Your raw data then can remain in its original format, so it avoids over-processing like you would get in a data warehouse. And you also have this notion of leaving data in place and just putting hooks into it. It can be highly effective then at query time because you can use the semantic model to understand the query patterns and to help you to derive algorithms that can look for what's inside there and can pull things back and check whether those were expected results or not. It provides a type of long-term value, so your older data that goes in your data lake can have a longer shelf life. You've built some context around it. That context can be shifted so it can retain its value over time. And I think one of the big things here is that it can handle the context of all of these different users. So when you build a data lake, oftentimes what happens is more and more people would like to put their data in, and then they would like to merge their data with other items, and they would like to find more complex patterns over time and be pulling answers out. And so one example that we run into a lot in the pharma and the biotech space is the perspectival difference between your scientists and your business users. They're working for the same company, but they have completely different ways of using the data lake, or completely different ideas of the types of patterns they would like to pull out, the analytics they'd like to run, and so on. So having said that, I'll now turn it back over to Eric Kavanaugh. Thanks very much, and looking forward to the rest of the discussion.
That sounds good. So let me go ahead and take control here of the slides, and I will hand it over. And let's bring in our first presenter from CASC. And by the way, let me go ahead and thank our sponsors today for allowing us to bring you this content free of charge and for underwriting our research. So Jonathan Gray is with us from CASC. So Jonathan, let me get your slide up and running here. There we go. Okay, so Jonathan, take it away. Tell us what this is all about, what you guys do for the data lake.
Great. Thanks a lot for having me and including me here in the panel. I talk about data lakes every day, so I'm excited to join this panel and kind of suss out what we all think what the future really holds. So CASC has a platform we call CDAP, the CASC Data Application Platform. And you can think of this as like a next generation integration framework. So we call it a unified integration platform that brings together the notion of data.
Hello. I think, John, you've got a VoIP problem going there, I think. Hello. Yeah, we lost you there for a second. Are you there? Whoa. Hold on. That is VoIP. Oh. Hold on, folks. We've got some technical difficulties going here. All right, Jonathan, are you back?
No, I'm here. I've been here. We can hear that, too.
Hold on a second. You calling it from a 617 number or 650?
Or a 650.
All right, so it looks like that was 617. Hold on. That was very strange. Okay. Hold on. Hold on. Whoa. Okay, I've isolated the problem. Okay, Jonathan, take it away. Sorry about that.
All right.
Someone had a VoIP problem.
Minor technical difficulties. We're all good. All right. So we're a unified integration platform, which is about bringing together the notion of data and applications. And that's a lot of kind of where we see data lakes is, data lakes are a lot about data, but ultimately the point is to write applications, to write Spark jobs, to generate analytics, to generate aggregations, to do machine learning, whatever the actual purpose of that data is. And by being a kind of integration layer, a middleware layer, what we do is we really try to address one of the big challenges we see in the market, which is enterprises are dealing with a lot of different infrastructure technologies in a lot of different environments. So they have multiple Hadoop distributions potentially, they have different NoSQL databases, they have Hadoop on-prem, they might have Hadoop in the cloud, they might be utilizing S3. They're utilizing all these different types of infrastructure systems, both on-prem and in the cloud. But each of the ways that they might manage the data lake concerns that we're talking about here, like self-service access and governance and metadata management and discoverability and schemas, those things are not necessarily built in cross-technology ways. And that's why we built CDAP and this architecture around the diagram that you see here, which we call our container architecture, which basically represents all of your data as a data set, all of your application logics, your SQL queries, and everything as a program, and you can package those things up into applications. And so when we kind of think about like some of the challenges that people have talked about, that Eric discussed, things like that, every data set has schema. And the default schema of a data set is basically schema-free in terms of it's a body, and it has completely untyped, bytes or string. And so the default is all data sits there in its raw form, but then I can create resultant data sets of that, or I can apply a view to a data set. And so it's really built around having this kind of schema on read, schema, everything has schema, but it starts out with just the basic schema, and then you can add views and add composite data sets and layer higher and higher level things on top of that raw data. And then the architecture basically allows you to apply security, governance, policy, operations, and management against the concepts of data sets, programs, and applications. And so it really separates what open source project a developer might use to build a certain solution or build a specific pipeline, and how the ops team and the administrators and the governance team and the security team actually have to deal with that infrastructure choice and that project choice. And so they adopt our architecture, and then they have pluggability in terms of which projects, which environments, which systems they want to use in the infrastructure layer.
All right, good stuff. Well, let's see. I don't know who we lost there, whose phone line went cattywampus on us, but let's go ahead and see. Cambridge Semantics is up next, and hopefully that was not the line that went crazy. So let's see. Sean Martin, are you out there?
I am. Good afternoon, and thank you very much for having me.
You bet.
Hopefully you can hear me.
Yes, I sure
Great,
can. Sound good.
Good. So my name's Sean Martin. I'm the CTO at Cambridge Semantics. And I guess very briefly, what you're looking at is a picture of our architecture. It in many ways echoes a lot of what we've seen already this evening, or this afternoon rather, both from Robin's slides and also Eric's. We, as Eric kind of implied, are a semantic technologies shop, so we worry a great deal about using open data standards, namely the ones from the W3C, things like RDF and OWL, to basically govern and deploy and operationalize everything related to a smart data lake. So we believe enormously in metadata and data, and often there's no difference between the two as we represent them using the semantic standards. Now, our architecture really is more than just a data lake that is about raw storage of data. It also provides a way to describe a logical warehouse using semantic models. And we also use the models to guide users, end users, to self-serve sophisticated queries and extracts from the data lake. I think if we look at the industries and how they're adopting this, I think the financial services industry is very interested in coming from the metadata-rich description of the data sources and using semantics to describe those, to do mappings from whatever the sort of arcane representations are in their data sources to semantic models to give a business meaning to the information as they bring it in, and to create large catalogs of the data sources. So you start to create that trail of provenance or lineage as you bring data right from the upstream data source through maybe some transformations and mappings to where it may end up in the data lake, either stored or just as a virtual data set that you can pull on the fly. So often that's where a financial industry customer would start, whereas on the pharma side, it's actually more or less the other side. It's on the consumption side, where end users now are able to use semantic models to guide their extractions for doing all manner of analytics across all sorts of varieties of data. The Cambridge Semantic System, we call it ANZO, obviously has tools for ingesting data, both structured and unstructured. For ingesting structured data, we use Spark, Apache Spark, which is where we generate the Scala code and the Spark jobs from semantic descriptions of the ETL that end users and data stewards, the owners of the data sources, if you like, create the mappings to the business meaning and whatever lightweight transformation they may need, and then we'll generate the Spark code. Because we operationalize the model's meaning, and we've operationalized the metadata models that describe the schema of the data, and we've captured semantically the description of the movement of data, we're also generating the provenance metadata as we go. The data then sits at rest in the data lake. There are catalogs, something we call a smart data catalog, with all kinds of metadata, including the ontologies that provide the business meaning of what is in that multi-dimensional data in each of the data sets. End users can browse that catalog and if you like, go shopping for data sets. And then we deploy an in-memory graph, call it a graph mart, but it's an in-memory graph technology, massively parallel, very scalable. We actually benchmarked at 1 trillion facts late last year. That we were able to deploy for individual users or groups of users who were spin up the data on demand into memory, and then they can do interactive analytics against it. And the interactive analytics are, there's no query languages to learn. You're just using dashboards or you're doing extractions for third-party tools like Tableau or best-of-breed BI tools. You're able to do those extractions yourself as an end user. So I think briefly, and then we do the same thing for unstructured data. We have pipelines that can read through enormous amounts of document data, do natural language processing on it, and the annotations that are extracted from documents are also made part of the graph and stored in the data lake and indexed. And that combination of data is what our end users are building solutions against. I think that kind of gives you what we do in a nutshell, and it's really a next generation data lake, and it's heavily oriented around graph. We're using graph technology, but to do everyday business analytics, often on combinations of tabular data. We're particularly adept at diverse and complex sets of relationships, which you want to do analytics or extraction.
Okay, good stuff. I love this diagram too, and I like the way you've put logical data warehouse in with the enterprise data lake and smart data discovery, right, which was necessary not just for data warehouses, but also for data lakes, and arguably more so for the data lake, which is going to be a bit more complex and multivariate, I suppose, than a data warehouse. So last but not least, let me show up here Unify's product architecture and hand it over to our presenter from Unify. Take it away. That's the other Sean.
Perfect. Thanks, Eric. Hopefully everybody can hear me okay. So I'm Sean Keenan. I run products at a company called Unify Software. Essentially what Unify is we're a data as a service platform that provides a user experience to line of business users within inside the enterprise to, one, search and discover any data entities or data sets that exist across any of the myriad of data sources we might be connected to, and then through that search and discovery experience, ultimately enabling users to take a subset of those data sets and provision them through our data preparation pillar of our platform for analysis, essentially. So to apply business rules, things like mashing up disparate data sources or enriching the data further or aggregating it and building derived metrics. That's kind of the data preparation side of our platform. From the data discovery side, which is our search and discovery experience, we support over 150 data sources, pretty much anything on-prem, whether it's a NoSQL or SQL data store, file systems with multi-structured and unstructured data, as well as pretty much any cloud-based data source, things like Salesforce, Marketo, the Weather Channel, Twitter, what have you. And how this relates to today's conversation is how we integrate with the data lake is we're built from the ground up for either a Hadoop or a Spark cluster, meaning that when a user goes into our data preparation pillar of our platform and says, hey, I'd like to join some data here sitting in S3 with maybe some data here in Oracle, we ultimately use the data lake to do that provisioning of the asset that the user is looking to do analysis. So in terms of building the data lake, how we make that happen is we don't come in on day one and say, hey, you need to move every single byte from all these various data sources into this environment before you can get value out of it. We build the data lake over time as users within inside these business units are using data to find relevant insights about their business. How we do that, this is essentially the architecture behind our product. We're a series of services with microservices underneath each one of these individual services. But essentially, through interacting with the data lake natively, you can see that we interact with pretty much any service that exists inside that ecosystem, whether it be the HDFS file system, whether it be MapReduce from an execution standpoint, whether it be Spark from an execution standpoint. We also have a service that we call our recommendation engine. This is where, through connecting the various data sources that we interact with, we run a series of heuristics and advanced analytic techniques against a random sample of data, against every single data set that exists inside those data sources to provide smart recommendations and automation to the end user as they actually work through our data preparation pillar of our application stack. So really our goal here at Unify is, one, we want to connect line of business users right to the data sources themselves and give them a real easy way to understand, hey, what data is in there and what is the state of that data before I actually choose to go use it. Then once I find some things of interest, Unify help me through a very simple kind of guided workflow of how I bring these disparate assets together and ultimately provision them for analysis, but do that in a very scalable way. So again, us being built on a microservices architecture, we can scale any one of our services independently or horizontally of one another, which allows us to run in the cloud in a very effective way, either in a single tenant or multi-tenant deployment model, depending on the customer's desires and what they're trying to essentially accomplish from a use case standpoint. So that's really Unify. That's essentially what we do. Again, data as a service application that's trying to enable the line of business users to more effectively be agile from an insight delivery perspective.
Okay, good. Let's go ahead and just jump into the roundtable here. We got a couple of really good questions from the audience. I'll throw the first one over to you, Sean, since we have your slide up here. On that left-hand side, you've got metadata store, and one of the attendees is asking a pretty compelling question here, saying from a practical perspective, how does the team extract metadata and tie it back to whatever categories or business entities they are trying to align it with? What does that process look like? Is it fully automated? Is it partially automated? What can people do to manage the metadata that gets brought in and make sure it's aligned properly?
Yeah, no, great question. So metadata management is its own single pillar within inside Unify. There is a bunch of automation that happens there. So first, we actually take every byte of metadata that any of the data sources that we connect to expose to us, whether it's an API, whether it's JDBC, whether it's ODBC, whether it's a file system or a series of files sitting in a S3 file system. We take every ounce of metadata that's exposed to us, we full text index it, and store it inside Unify. We also, through the series of profiling and heuristics we run against a random sample of every asset inside those data sources, generate a significant amount of data, metadata, about the data itself. That also gets stored in Unify's Metastore, and we're constantly capturing metadata as users actually use our application. That metadata is available to any user of the application. They can annotate it even further with more business ontology if they want to actually put the business acumen around these maybe what could be technical assets in nature. Or we have an open API at every layer of our app. We can actually ingest that from any other Metastore that a client might be running, or maybe over the years they've put all their business definitions inside Excel. Well, great. We'll bring that right into Unify, and it's available across every single layer of our application.
Yeah, that's interesting. And could you talk a bit more about microservices and how they work in your platform for anyone who might not be familiar with that? This is the new, interesting, cool way of doing enterprise computing. It's kind of like the evolution of SOA, at least as I see it. But can you get some context around microservices with respect to what you're doing here?
Yeah, for sure. So that was a decision we made up front, and as you indicated there, Eric, it is kind of the next generation of enterprise software and enterprise systems are being architected in this way. And there's a number of benefits to that. One is flexibility. As I mentioned earlier, we can really scale any one of our services that are part of our core application stack independently of one another. So if there was a use case where maybe the client had very low latency, kind of high throughput requirements, and we were going to be running thousands of jobs every single day, well, then we might scale our executor service to be able to accommodate that type of workload independently of maybe the user interface, because maybe there's only 10 users versus 1,000 users for that typical scenario. The second reason we did that is because of agility. We're 2 years in post-GA of the product, and we're still doing 6 releases of the product. So us being able to actually work on one core component of the product without affecting other areas of the application provides us significant agility to actually be able to deliver features in a very quick period of time and be constantly innovating around the product in a very agile fashion.
Yeah, and what does the footprint look like? So when a customer says, you guys have what I want for our data lake, they bring you in, how does that actually get installed? I presume it's installed on premises, but what are the components that get installed? How long does that take? Give us some context there.
Yeah, so most of our customers are running in the cloud. We do have an on-premise product, and we do have some customers leveraging that. And we can deploy in pretty much any number of ways. We can run on any cloud provider. We have automation across the primary cloud providers. Or we can actually host the entire service on behalf of the client. It really all depends on kind of what they're looking for. And from an installation and configuration standpoint, obviously that varies if we're doing an on-prem install versus maybe an implementation where we own it soup to nuts. If it's a soup to nuts implementation, a user could log into unifysoftware.com and be off and running in less than 15 minutes with literally a Spark cluster and a Hadoop cluster and everything required to deliver this experience provision behind it. If it's on-prem, well, then we'll work with whatever existing investment the cluster's made and either the customer's made in a Hadoop distribution, or maybe they went with Databricks from a Spark implementation standpoint. We support all of that natively as well.
Okay, good. Let me go ahead and bring in the other Sean on our webcast today, Sean Martin from Cambridge Semantics, and just kind of talk about the same issues here a little bit maybe. How big a deal is metadata in your environment? And what are some standard use cases that you see out there for the technology?
Metadata is obviously everything that makes apart from the data itself, what makes the smart data lake a smart data lake. We start right at the upstream, as I mentioned before, where we will extract the catalogs from the sources and create a metadata layer out of the schema that describes the source of the data. And then, because we're using semantic technologies, we can annotate that metadata, which is now in a graph form. We can annotate it with anything that a customer cares about. So maybe it's around policy, maybe it's around quality, maybe it's around regulations that apply to that data. Maybe it's about how often that data is used, or the context of the data. What else depends on that data? So right at the very beginning, we've got information that customers can layer on top as metadata. On top of that, we obviously try to automatically determine metadata from the content, so the type of the data, the semantic type of the data, and information sampled from the content of the data around completeness and what kind of values that you've got, ranges, and that kind of thing. Then the next layer of metadata describes the mappings between the schema, for the raw data, and the models of meaning, which are really the business view of what information means. So those ontologies really describe from the business's point of view their vocabulary, the entities and the attributes and the relationships that are attributes between entities. That's another layer of metadata that customers can annotate the schema with. And now that combination can be used to generate the ETL jobs to actually ingest the data and put it into the graph, and then register in the catalog, which is yet more metadata layered on top of it. And then users can just use that metadata to help them locate information about what it means, or where it came from, or what it depended on, or how much it cost, or really any dimension that you want to query. Because we're using semantic standards, this is obviously all read and writable and queryable using Sparkle, which is the query language.
Okay, good. And let me, last but not least, let's bring in Jonathan here. Here's a good question for you. One of the attendees is asking, how do you architect a real-time ingestion into the lake with governance, but still provide enough throughput such that the ingested data is not hugely queued up? Can you kind of talk about how you manage the fire hose effectively?
Yeah, I mean, I think it depends on exactly, what you're talking about. A lot of the use cases, we have a lot of streaming ingest use cases, but metadata tends to be associated with, from a governance standpoint and everything, the feed itself versus necessarily each individual event. So I don't necessarily look at the managing of that throughput and scale and stuff as related to the governance side of it. I think the thing that we see when it comes to streaming, ingest, and it comes to real-time and stuff is that the technical challenges around scale and performance are a lot more prevalent when things are in batch it just might take longer, but ultimately your expectation is it's offline. But when things are real time, then it's really important that all of a sudden, if your downstream databases are unavailable, that upstream there's some way for it to deal with it. And so what we end up seeing is when people go from batch to real time, they kind of reset the clock and it's a new infrastructure project. And so they're kind of out of the world of data management and out of the world of ETL and data integration and more in the world of how do I build a high throughput ingest system? And that's a lot of where we focus is, how do you provide higher level capabilities? So if somebody has a Kafka infrastructure, how do you make it so that there's a very simple way to plug that Kafka infrastructure into the data lake to, maybe automatically pull specific topics, automatically add the metadata associated with them downstream. And so I think it's really, figuring out how do you take the open source projects and the existing, ESBs and all of that ecosystem of real-time and event buses and get them into the data lake in some way that is simple from a technology standpoint. And I don't know if the metadata concerns, at least for our customers, have been especially the challenge.
Yeah, right. It's interesting. In the database world, we have this curious concept called archiving, which is largely executed in fits and starts. At what point do organizations need to start thinking about archiving with respect to a data lake? Because obviously, we're talking about large amounts of data, usually. We're talking about different kinds of data, not just the traditional highly structured, if you will, data of a relational database. You're talking about a lot of raw data. Is archiving a concern yet, or should it be in the near future? What do you think about that?
Yeah, I think it is a concern. I think that the public cloud is going to help a lot with that, and people are going to start utilizing the public cloud to provide that. I'd say the thing that we see is if a data lake actually becomes something that's business critical, so if I am ingesting data from third parties and applying various processes to that and serving it back up to my customers, if I'm offering my customers some kind of SLA or some kind of guarantee, or there's some expectation of I'm going to deliver this to you within a certain amount of time, well, if I'm using a data lake to get that done.
Hi, this is Robin.
Now I'm in.
Sorry, go ahead.
I'm in the world of disaster recovery. I'm in the world of highly available infrastructure. And so the thing that we actually see is less archiving and more, hey, I need a warm or cold disaster recovery cluster for my data lake. I need to actually say if this thing goes down, and I know from experience it's going to take 6 hours to come back up again if I have some fatal problem, I'll break all my SLAs to my customers. So I need another path. So I need a second cluster. I need a backup, not as archive, as actually disaster recovery, as high availability. That's the thing that we actually see as data lakes are they're not just an archive, right? They're really being used for real use cases that actually become business critical.
Right.
So
that's right.
That's where a lot of our development today is for some of our big customers around disaster recovery and replication and resiliency. And all of a sudden, when you're not batch and you're real time, well, you need rolling upgrades and you need all of these capabilities of kind of traditional application systems, not just back-end, offline data warehouses.
That's right. Okay, good. Well, let's get some closing comments maybe from Dr. Little. I think Dr. Bloor had a hard stop there at the top of the hour. But Dr. Little, any closing comments from you? What did you think about the technology showcase today or the questions? What do you think?
Really interesting. Nicely done by everyone. I would like to say one thing, Eric, about your last question, your last point about the data lake and archiving. One thing that's very interesting is that as the technology matures, one of the areas, though, where you're still going to need to consider a specific kind of archiving is in highly regulated industries. So our company does a lot of work in the pharma and biotech, as I mentioned, and part of the issue there is that your data has to be maintained for 30 years. And so archiving is a big deal. So if you start introducing these new kinds of data lakes and you're using it for more of this transactional stuff, or you're using it for a lot of your day-to-day master data, your analytics, and these kinds of things, that's great, but there is a need for still a type of archiving so that if something happens in the FDA, for example, or the EPA, or Fish and Wildlife, or USDA has to go in and say, hey, you need to supply this data from 10 or 15 or 20 years ago, that is still a concern in these kinds of industries.
Mm-hmm. I believe so. Well, folks, we burned through a solid hour here of great content. Big thanks to all of our attendees today for your time and effort checking out our webcast, and for all the fantastic questions. I have to say, a lot of really good pointed questions. We'll be sure to pass those on to our presenters today. Big thanks again to all of our sponsors, to CAST, to Cambridge Semantics, and to Unify, and to all their speakers for dialing in. Cool stuff. We're just at the beginning of the data lake journey, I can promise you that, but well begun is half done. That's one of my favorite expressions, favorite cliches. If you really think through this stuff, you're going to be a lot better off in a year or 2 years down the road. But everything is changing, so keep tuning into these webcasts, folks, and we'll keep you up to date with all the very latest. And like I say, we're going to have a findings webcast next month. So if you have any thoughts or comments or anything you'd like to learn for sure in that report, send me an email, info@insightanalysis.com. And with that, we're going to bid you all farewell, folks. Thanks again. Talk to you next time. Talk to you next week. Take care. Bye-bye.